All right, in section 4, we're going to go back and review a topic from Algebra 2, which is about logarithms. So the idea of a logarithm is really a different way to explain or represent an exponent. So obviously it's very, very related to exponential form. For example, if I have 2 to the second power equals 4, we all know that's true. This is a logarithm. That exponent is a logarithm. All exponents are logarithms. If to the x equal 5, this exponent is some kind of logarithm. All logarithms they are a fancy way to write an exponent. And we have the buttons in the calculator that can find what those values are. So the idea is this. You have this idea of an exponential form, which we've been talking about, right? So let's represent it as y equals b to the x as listed on your notes. So essentially we have a couple parts of this. So if you think about it, we have the y equals, we have the b, and we have the x. So I'm going to give all these fancy names. So the x is obviously the exponent. That's kind of a pretty universally accepted thing, exponent. The b here we're going to call the base. It's the base of the exponential. Now y is kind of interesting. So if you do y equal to b of x, you could call it the value. The fancy name for it is the argument. So the value that's going to be there, I'm going to call it the argument. So I have A, E, and B. Okay? So the idea is I have this exponent, and I'm saying all logs are exponent. So what I'm claiming is I can write this exponent by itself. So I can write x by itself. So if you have an exponent, it's always equal to log of something. So in logs, we have two numbers. We have a base, and we have a value, which we'll eventually call the argument, not surprisingly. So the base is going to be b, and the argument is going to be y, as you see here. So things get rearranged. The exponent is always a log, so it goes by itself. The base of the exponential is the base of the log, and then this argument value will go right here. So this rearrangement will give us a log value. Now, what is the benefit of doing this? Let's switch a couple, and I'll show you what the benefit is. So if I look at this first one, I have 2 squared equals 4. Everyone knows that's true. So if I say 2 squared equals 4, I can rewrite this saying 2, which is the exponent, equals log base 2, because the base 2 here, of our argument, which is 4. So log base 2 of 4 is 2. So really we'll talk a little bit about later on how we find a log and how we can kind of figure out how we define this. Same thing for the next one. We have 3 to the negative 4 equals 181st. That's fine. So that negative 4 is an exponent, so all exponents can be written as logs. So this is going to be log base 3 of 181st. So I promise if you typed log base 181st in your calculator, you would get negative 4. If you type log base 2 of 4 in your calculator, you would get 2. So let's look at the next one. And this is where logs can really help us, because if you look at this, we have 4 to the x equals 16. So if we have 4 to the x equals 16 and we rewrite it, the exponent x can equal log base 4 of 16. So that's the rewrite, and we could certainly put that in our calculator. Now we can also think about this. 4 to what power is 16? Well, I know in this problem x is 2, because 4 squared is 16. So I know by definition log base 4 of 16 is simply going to be 2. Now that's obviously something I could have solved this equation without using logs, but other ones we don't get so lucky. So if we look at the last one here, we have 2 to the x equals 7. So if I rewrite that, the exponent is x equals log base 2 of 7. Now, I have no idea what log base 2 of 7. 2 to no power, nice power, is going to equal 7, so I'm kind of stuck. So, but whatever this value is, it is this number. Log base 2 of 7 is a number. It's just not a number that we know very readily. So we'll see eventually how we can find those values. Now, if you have something in log, you can also switch it to exponential. So we obviously were turning it from exponential to log, but we can go both ways. So if I'm turning this from log, well, the base of this log is 7. Well, remember, the log always equals the exponent. So this is 7 to the third equals 343. And of course, 7 to the third is 343, because 7 times itself 3 times is 343. Same idea for the next one. We have log base 5 of 1/625. So it's base to the exponent. Exponent's always what a log equals. 1/625. All right, finally, same thing for the last one. We have 4 to the 7th. It's the base to the exponent, always what a log equals y. So the last one had a variable in it, so switching to exponential form actually got that variable by itself. Like most equation solving, we like when the variable's by itself. That's kind of one of the big goals in solving equations. So obviously we will have a lot of logarithms and things like that we're trying to evaluate. Now some of these we can certainly do without a calculator. Because in general, if we think about a log is an exponent, right? So when you talk about a log, it's really going to be the exponent. You raise the base to. This is the same thing that was on the previous page. To get the argument, which is the value inside the log. So if I say log base 6 of 36, these are all really easy ones. So all this means is six to what power is 36? Well, we know 6 squared is 36, so log base 6 of 36 is 2. So thinking of a log expression, you're really just trying to think of what power you'd raise the base to get that argument value. Now you can do this for all these. Now some are obviously not as nice. These are all really nice, so ones we can certainly do in our head. 2 to what power is 128 is the log of base 2 of 28. So we have to know how many times do I have to multiply 2 to get 128. And if I start multiplying 2's, it turns out I need to do that 7 times. Now the next one's interesting. It says log of 1/100th. There is no base. If you see the word log and there's no base, we always assume it's base 10 because we are in a base 10 world. So this essentially is 10 to what power is 1 over 100. Right away, based on what I know from before, I know this has to be negative. Because if I'm going to take a number to a power and get a fraction, it has to be negative. So it has to be negative, and then 10 times 10 is 100, so it is negative 2. Same thing for this one. This one says 16 to what power is 2. Well, 16 to what power is 2? We need it to get smaller, so it has to be a fractional exponent. We know the square root of 16 is 4, so the fourth root of 16 is 2. So log base 16 of 2 is 1/4 or 0.25. Last one, we have a log base 6 of 1. That's going to be 6 to what power is 1, and the only thing you raise a power to and get 1 is 0. So 6 to the log base 6 of 1 equals 0. You can certainly type these in the calculator and double check your work. You can type in Desmos, you can do things like that. Now to type these in a calculator, we don't always have these log buttons, so we'll have to do it a special way. Now we have all these different types of logarithms. There is another special logarithm that will occur sometimes, and that is what's called a natural logarithm. Now a natural logarithm is just going to be a log with a base of e. We talked about e earlier with the graphing. We talked about e as one of our growth equations when we're continuously growing something. So e occurs a lot. So the way we see that a natural logarithm is usually right with ln. So it doesn't have the log, it typically just has the ln. So whenever you see ln, it really is kind of something with this magical e. So you can always write the little e down here when I see ln, because I know that means base e. So these are in logs, so if I'm going to convert this, we know that this is my exponent, because logs always equal the exponent. So I could convert this to e to the fourth equals x. So even though that base is not there, it really is there. Same thing when you're doing ln of 10. ln of 10, we don't know the base, but I do know this e. So if I wanted to change forms, this is my exponent, so it's e to the x equals 10. Now this would seem like a worse form because now the variable is not by itself, and we typically like the variable by itself. But if you're switching forms, then that's just fine. Now you can also switch things with e, so when you have an e and you're switching them, you could simply use the natural log. So when I look at this, I have e to the x equal 50. So e to the x equal 50, if I change it to log, it's going to be log base e, and this exponent will go by itself. So I know x will go by itself, and it's log base e, but I don't have to write the e, I can just write ln. ln assumes it's base e. So x equals ln of 50. Same idea over here. Remember, when you're switching it to log form, the exponent is always equal to the log. So it's 0.5 equals natural log, because it's base e, of x. Now, if you want to write the e down here to make yourself feel better, that's absolutely fine, but it's not necessary. ln in itself will assume that it is e. Now, things with natural logs are pretty tough to do by hand, so typically we use a calculator. So if I go to my calculator, there is an ln button. So if you see ln on your calculator, you can literally type in ln64. And that is going to give me 4.16 if I go to 2 decimals. So what that means is e to the 4.16-ish is about 64. You can check it and see what it means, but that's what a log is. Log is the exponent that you raise the base to get that value. Log of 1/3 I could do as well. I'm just going to type it in, ln of 1/3. And this one turns out to be approximately negative 1.10 if you went to 2 decimal places. Now, other ones you might have to put in, like in Desmos, you can put any log in, but if you have a regular old calculator, some other logs can be a little difficult to put in, so we should probably talk about that. So let's say I had log base 2 of 11. Now, there is a log button on the calculator, but that log button doesn't allow us to put this base in. That's a problem. So if you want to put this in a generic calculator, you usually have to do log of 11 divided by log of 2. So you actually have to write it as 2 logs divided. Log of the value up here and the base below. Now, if you're using a newer calculator like Desmos, some of the TI calculators have features where you do not have to do this. But if you're doing a general standard calculator or a phone calculator, then this is the way you have to do this, and this becomes 3.46. So, pretty okay, not too terrible. So just find these log values, but if you have questions, obviously, please do let me know.